Sargent, and this is lesson 1.3, Measurement and Scientific Notation. So when we look at measurement, there are two types of measurement: qualitative measurement and quantitative measurement. Qualitative measurement is a descriptive, non-numerical measurement, which means that there are going to be no numbers. The problem with qualitative measurement is that there is personal influences or perception that can result in different descriptions. For instance, if you've ever gone to your parents or someone and said, "Man, I really feel like I'm just burning up," and you ask them to feel your forehead, they might say, "No, you really don't feel hot, but you feel like you do." Or you could have two different people feel your forehead. One person that just came from gym and they don't think you're hot at all, and someone else that came from a really cold classroom and they could think that you were burning up. Same goes for an object that is heavy for one person may feel relatively light to another person. Quantitative measurement is a definite measurement, and it is always going to have numbers and units. Throughout the year, anytime you have a number, you must label it with the correct units. A number by itself does not mean anything. The problem with quantitative measurement is that the measurements are only as reliable as the instrument used to measure it with. So we have a beaker and a graduated cylinder. The beaker is a 200 milliliter beaker, and you can see these markings or graduations at every 25 milliliters. With the graduated cylinder, there are graduations at every 10th of a milliliter. So if I needed 8.5 milliliters of water, my best bet is to use the graduated cylinder to measure that versus the beaker. So we looked at this object in class, and this is a ball that as you toss it up, it changes colors, and you can toss it back and it will go back to the blue. I want you to take a look at it, and I want you to make 3 qualitative and 3 quantitative measurements. So for qualitative, you might say that the ball is blue, that it can change to purple. You can say that there are ridges on the blue. You can say that there are holes in it. All of those things would describe it. You could also say that the size is similar to a softball or some other object that you can compare it to. For quantitative measurements, we could measure the circumference, the diameter, radius. We can determine the weight of it or the mass. All of these are going to have a specific number and unit that go with them. So that's the difference between qualitative and quantitative measurements. Something else that we need to look at is these are some numbers that we use in chemistry. 1 atom of gold weighs point, and then we have all these zeros, 327 grams. There's 3, 6, 9, 12, 15, 18, 21 zeros, and then 327. That is the mass of 1 atom of gold. 1 gram of hydrogen is 602 with 3, 6, 9, 12, 15, 18, 21 zeros behind it. There's that many atoms in 1 gram of hydrogen. So these numbers have a lot of zeros in them. So sometimes we use scientific notation. And scientific notation, we use that because they are very small or very large. The numbers are very small or large. This makes it easier to work with those numbers. So let's just review using scientific notation. A scientific notation is a number that includes a coefficient, which is the number in front of the decimal. That needs to be greater than 1 and less than 10. And then you will multiply that by 10 raised to a power. So we have 105 and we have 6 zeros behind it. Anytime you have a whole number, you are going to assume that the decimal is at the end. And we need to move it until we have something between 1 and 10 in front of the decimal. So 1, 2, 3, 4, 5, 6, 7, 8 places is how many. So we're going to have 1.05 times 10 to the 8th. Here we have 0.0000562. So again, we need to move the decimal, but this time we're moving it to the right till we have something in front of the decimal that is between 1 and 10. So 1, 2, 3, 4, 5. So this is going to be 5.62, excuse me, times 10. We moved our decimal 5 places, but we moved it in the opposite direction, so it's to the -5th. So for numbers that are greater than 10, you are going to move the decimal to the left, and the exponent is going to be positive. For numbers that are less than 1, and I know yours says 10, go ahead and cross out that 0 and make it 1. Move the decimal to the right, and the exponent is negative. Accuracy and precision. So accuracy is how close a measurement comes to the actual or the accepted value. Precision is how close a series of measurements are to one another. And this is possible by making more markings on your measuring device. So we have 3 targets here, and if the goal is to hit the bullseye, we want to determine if they have accuracy or precision or both or neither. So in our first one, all 3 are at the bullseye, so we have yes to accuracy. And all 3 are close together, so yes to precision. On the middle target, we're not near the bullseye, so no to accuracy. And then, but all 3 are close together, so yes to precision. And here in our last target, none of them are hitting the bullseye, so we have no accuracy. And then all 3 are spread out, so no to precision. So there are 2 types of error that we need to look at, and error equals the experimental value minus the accepted value. So experimental is what you measure, accepted is the known value. So positive error means that you measure slightly over. Negative error means that you measured slightly under. For percent error, we're going to use the absolute value bars. And again, take the experimental minus the accepted, but because those absolute value bars, that'll make it positive, divided by the accepted, and then multiply by 100 to get a percentage. So can percent error be negative? No, because of the absolute value bars. So if the accepted value for boiling water is 100 degrees Celsius, and you measured the temperature to be 99.1 degrees Celsius, we want to determine the error of our measurement. So error equals experimental minus accepted. So we measured it to be 99.1 degrees Celsius. The accepted value is 100.0 degrees Celsius. So that gives us a difference of negative 0.9 degrees Celsius. So then when we do percent error, we have the absolute value of the experimental minus the accepted divided by the accepted times 100. So we have 99.1 degrees Celsius minus 100.0 degrees Celsius divided by 100.0 degrees Celsius times 100. These 100s actually are going to cancel out, so we have 0.9% error. So what do you think some of the reasons for the error in measurement are going to be? Do not just say human error. Say what the human error could be, in that you read the thermometer incorrectly. You could have been looking down on it or looking up at it, which would have caused a false reading. You could have contamination in the water. You could have simply just measured the boiling temp before it fully started boiling. All of those things are reasons that you did not measure it to be 100 degrees Celsius. So explain that with your labs this year. So that's the end. You have practice over measurement and scientific notation at the bottom of page 8 and the top of page 9. Go ahead and take a look at that and stop by and ask me if you have any questions. Thanks for stopping by. Have a great day.